Every bit of energy that you're not running through a wet cooling tower saves you water, so that's a multiplied effect. And how do we do that? One very good way is making sure that you seal your doors and windows, elevator shafts, and also your stairwells. Making sure that you have setback schedules and that they're appropriate to the occupancy of the building. Airside economizing is so good an idea, you're going to see it come back again when I talk about shifting loads. Recommissioning or retrocommissioning your HVAC systems, make sure that they're doing what you want them to do. Balancing the building. You don't want to be blowing the air outside, the conditioned air, outside of the zone that it's intended to be in. And then, last but far from least, is keeping a preventive maintenance schedule. Moving on to the systems level. First approach is match the loads with your systems. And that is breaking out specialty areas that are the minority load for your building, but sometimes have longer run hours or have high occupancy that's intermittent. For example, server rooms tend to be a very good application here to maybe have that served by an entirely different cooling system so that you're not dragging your whole building chiller into availability throughout the clock, around the clock, because you have, a server room on the first floor. Next, we're shifting the loads, so matching the loads, then going to shifting the loads. Mainly what I mean here is you've minimized your loads and you've done what you can to match the equipment to the loads. Now you want to shift the cooling to as efficient a way as you can do it. How do we do that? The first one, like I said, airside economizing always comes up as a prime candidate. If you can cool with your outside air, you don't need to run your chiller, you don't need to run your cooling tower, at least not as much. And in this climate, it's exceptionally good. Next, water side economizing. Here you're shifting chiller load to the cooling tower, and it can let you shut down your chiller some of the time during part load seasons. There are two ways to do that. You can add a plate and frame heat exchanger to an open cooling tower or replace the cooling tower with a closed loop fluid cooler. Here's an example of the plate and frame heat exchanger here in between your chilled water, so bypassing the chiller where you can and then rejecting that heat via the cooling tower. I didn't come up with a slide for the closed loop fluid cooler, but basically to do that you're eliminating the plate and frame and going directly to the fluid cooler with the chilled water and then having the condenser water just circulate internally here. Variable speed drives, motors abide by fan laws or pump laws, affinity laws, which is a 1/3 power law, meaning if you slow down the motor a little bit, you can save a lot in the power department. It also has the added benefit of extending the motor life because it's not an abrupt on-off. So here's just a diagram of the 1/3 power law or the affinity law. So you can see that if you're at 90%, just slowing it down 10% when you can, that you're down at about 72% power. If you slow it down 20%, you're right around 50% power. And if anyone's ever seen a cooling tower fan running at 30% or at about 20 hertz, it's just going like this. And that is, when I've seen it, it kind of looks like it's just, on natural draft and it's just coasting. Well, when I look at it around 30%, it makes it look a lot better to my eye too, on an energy standpoint. Looking at the chiller itself, we want to make sure that you fit it to the load that it's trying to handle, but also to the load profile, so that it's sized appropriately, but also that it can stage on the compressor rate, or it has a variable speed compressor, or like a multi-stack, that it's modular, and that the stages can be added appropriate to the loading, so you don't have one big honking single stage chiller. Going on to the focus here with the cooling tower, induced draft might have benefits here because axial fans tend to be more efficient than centrifugal. You have less of an opportunity to have freeze problems. They might be a little noisier, but you can see just by the geometry, here's your forced draft cooling tower, and here's your induced draft. It'll eject the water at a greater velocity, the steam at a greater velocity here, so you have less re-entry problems here, recirculation, and that also, in cold weather, then prevents a lot of your freeze problems. If you oversize your cooling tower, that means that you don't have to pump it as much, or maybe not necessarily the condenser water, or you don't necessarily have to run the fans as hard to do so. So you can save pumping and fan energy if you have the real estate and capital expense to do that, then that can work for you. You want to have a bypass that's inside your building, or at least if you're going to, when your cooling tower's on and off in your shoulder seasons, you want to be able to damper it off or prevent airflow from going through there, because even though you don't have your spray pumps going, you don't have your fans going, you'll have natural convection drawing the water out of, or the heat out of the condenser water. I had one building that I looked at that they were losing half a degree, and then it'd go back down into their building, down to their boiler, their electric boiler, so it's a direct heat impact that they're heating and cooling at the same time, and they're defeating themselves. Once again, with the VSDs, on your fans, if one idea that's particularly useful is in your cooling tower, if you have multiple cells, run all of the fans at the same time rather than staging them. Here's an example of a 2-cell tower. If there's a 100 horsepower fan in each one of them, but you're only at 50% heat load or cooling load, then if you ran one fan, it'd run 100 horsepower at full speed. If you ran both cells, but you could run them both at half speed, you'd be down at a quarter of that horsepower. Again, that's the old power law. Have controls, and I know that sounds moronic almost, but there are still buildings out there that operate by local mercury thermostats and breakers to turn equipment on and off. That's fine, it works, but it's not great. And these buildings that are operating that way are operating essentially in the blind. They don't have diagnostics as far as when they're bleeding their energy away and when when they're operating inefficiently. They don't have signals that go on when something's failed or on the verge of failing. So have a building energy management system, one with good graphics. By good graphics, I mean a very intuitive schematic, and also clear information on the flows and the operation of everything. Schedules that enable the equipment to run when it should be during occupied times, and then also sequences of operations, the real brains of things. Have it be clear. For example, the staging of your cooling tower, that your spray pumps go on first, and then you start either staging your fans on or running your variable speed drive up to it. Needs to have alarms and also trend logging, so that you can identify why is it that now I'm using more power than I did yesterday when the temperature was the same outside and the occupancy was the same. Scheduling, make sure that you have your setbacks clear with your current occupancy and your equipment operation. Resetting temperatures as far as the operation of your chiller. Your chiller is designed for, a lot of chillers are designed for peak operation, peak chilling capacity, which is a very small portion of the year. Most of the time, you're under peak loading. During those times, you may be able to raise the chilled water temperature, get the cooling that you need in the space for thermal comfort, and your chiller won't have to fight as hard. So if you raise that chilled water temperature, its efficiency is improved. And it's especially effective when you couple it with water side economizing, because then when you have a water side economizer, then it can reach your chilled water temperatures, if they're higher, more often, which equates to more chiller downtime, shutdown time. Also, you can use it with chilled water beams and panels, which don't require as cold a temperature in your building. Another angle is condenser water temperature reset, which is lowering the condenser water temperature below 85 or 84. And that's, once again, when you're not at peak condition, or if you have a larger oversized cooling tower, then you'll improve your chiller efficiency, and you can actually slow down your condenser water pump, and again take advantage of the 1/3 power law. Why do I care about maintenance? Why do you care about maintenance? Your cooling tower is a heat transfer device. Anything that you can do to keep it operating in stellar performance is going to be better for you. Anything where you slack off on allowing your heat transfer device to transfer heat is going to cost you energy and can cost you water as well. The fans have to work harder, the pumps have to work harder, and they have to run longer. The villains: poor heat transfer, poor airflow, poor water flow. Here's some pictures. Here are some other pictures. Under poor heat transfer, scale, corrosion, particulates, dust, and organic interfere with the heat transfer capability, whether it be in the cooling tower air side or the water side in the pipes. Also, poor airflow. You can have debris clogging up the inlets, the filters. You want to make sure that your fans are solidly mounted, aligned well, the gearbox is connected right, and your fan pitch is right, and check for damage and vibration. For pumps, it's very similar to that, although you want to check also your strainers are clear. Okay, so we had villains. We need to have some heroes here, and I can't keep those guys up on the screen because I keep staring at them. So maintain your equipment, make sure it's operating the way it's intended, and keep up your water quality. And that includes filtering it. Have a filtration system, keep it up. Have your water treatment system so that it's appropriate to your uses, keep it up. Keep up your testing, keep up your calibration of your instruments so that what they're reading is actually, or what they're telling you is actually what's the truth. And keep in mind that because it's a heat transfer device, if you have a good system and you keep it clean, you're going to keep transferring the heat the way that you need to. It's going to save energy, but it's also going to save water because you're going to have less run time, trying to reject that heat. Some resources are the Cooling Tower Institute. The manufacturers, some of them have online calculators, designers, and then talking to your local electric utility, as far as another motivator, which is what I do. I give rebates for energy efficiency improvements. So we'll go ahead and take a look at, for example, one building I had wanted to add variable speed drives to their cooling tower and controls on them and stuff, and they ended up, I wasn't able to connect and get the actual numbers, but I think we gave them something like a $60,000 rebate on a collective overall $150,000 project, something like that. So they can be very sizable, and it's worth making contact with your utility. Here's some contact information, and I invite any questions.